Hi, so welcome to another review video. Today we're going to talk about acids and bases, starting with our definitions. Acids donate protons. You want to recognize H plus as both a hydrogen ion and a proton. Just a reminder that it's a proton because it's lost its one electron, so it only has one proton and maybe one neutron. Protons can join with water to make H3O plus, which is our hydronium ion. You're going to want to recognize the name as well as the polyatomic ion formula. Acids can take on several different forms. We have our generic inorganic acid form, which is HA. You're going to see it like this on your reference sheet for our equilibrium constant for acids. COOH ending, the H at the end is the acidic H, and this is our organic carboxylic acids. We also have NH4 plus here, which is our ammonium ion. I've added this polyatomic ion because it is the conjugate acid of ammonia, which you can see down here, NH3. And I just want to include an example of a conjugate acid just to keep in mind. Bases, proton acceptor, so H plus acceptor, that's our Bronsted-Lowry definition. They also donate hydroxide ions, another polyatomic ion you're definitely going to want to remember, which is our Arrhenius definition. Most commonly we see group 1, group 2 hydroxides like sodium hydroxide, but ammonia is a very common weak base. We've also talked about this term strength. People tend to mix this up with thinking it always means the highest pHs for bases and the lowest pHs for acids. That's not always the case. pH is based on the concentration of your solution. Strong is simply describing how much that substance can ionize. We're going to treat it like a straightforward stoichiometry problem because if you take a look at our dissociation equations, we have an arrow pointing in one direction. That means I expect HNO3 to completely turn into only hydrogen ions and nitrate ions in solution. I don't expect to have any more HNO3 once it's done dissolving. Same thing with our strong hydroxides. I expect them to fully dissociate. You should know your strong acids and strong bases. It's a need to memorize piece of information. And here I have the strong acids and our strong bases listed in the boxes. So to go along with our strong acids and bases, we also have weak acids and bases, meaning they only partially dissociate. This is any acid or base that is not listed in those two boxes. So most acids and bases are quite weak, and this is where equilibrium is going to come in. So because these substances partially dissociate, we are using an equilibrium problem. It is a straightforward equilibrium problem like we've already done. It sounds more complicated because it's an acid or a base, but ultimately we still need an equilibrium constant. We're going to call it Ka for acids, Kb for bases, but it's just an equilibrium constant, which means all of those factors we've talked about with K, manipulations of K, K, if it's very large, so bigger than 1, means we're going towards the product side of our equilibrium. If K is very small, it's going towards the reactant side of our equation. We can also do Q and K comparisons for acids and bases. Everything we learned from equilibrium still applies here. Now if we take a look, here's our generic dissociation equations. It follows the same format for every weak base and weak acid. The Ka is given to you on the periodic table, but your equations sheet, and Kb follows the similar format. The key thing to keep in mind with bases is you're actually solving for that hydroxide ion concentration, when you use an ICE table as opposed to solving for the H plus or the proton concentration, which means for weak acids, once you solve that ICE table, you can go straight into solving for the pH. But if you're dealing with a base, you're going to go straight into POH. Which means from a solving standpoint, we're going to have one more step with our weak base. Because we solve for the hydroxide concentration, we have to remember that pH plus POH equals 14. So we can easily swap in between POH and pH as long as we remember we have this equation. Another very useful equation to keep in mind is you can go between weak bases and weak acids K values. We just have to remember we have Ka times Kb equals Kw. I believe this is also on your equation sheet, but this relationship allows us to compare water, 1 times 10 to the negative 14th at 25 degrees Celsius, and if we're given the Ka, we can solve for the Kb value. If we're given the Kb, we can solve for the Ka value. So we can use math, manipulate our equation as we need, and you do end up using this equation in the practice sheet. We also started comparing the strengths of acids based on their structure and what they are doing in solution. If we take a look, I have our generic equation in the top right hand corner. Just a reminder, again, we can apply all that we know about the equilibrium constant from our last review and use it here. So if we have a large K, that means we favor the products. We're shifting towards the ions in solution, favoring the forward reaction. This also corresponds to a small pKa, so it's just useful to remember that Ka and pKa are an inverse relationship. This means you took the negative log of Ka, but this means more dissociation, which would mean a strong acid. Strong acids dissociate completely, ionize completely. That means they strongly favor having ions in solution and have very, very large K values. Therefore, it's probably fairly likely you'll have a question where you might have to compare Ka or pKa values. Just know that the smaller the pKa value, the stronger that acid is. The bigger your Ka value, the stronger your acid is. One way or the other, and you compare these values between different acids. Another way to look at strong acids is they have a weak conjugate base. This means the strong acid is very good at dissociating, whereas its weak conjugate base is not good at picking up a proton. For example, here's our strong acid. So here's our acid. I decided to rewrite it with water in there just to make it a little more obvious where the base is, but our acid is donating a proton. Water is acting as our base. Remember that water is amphoteric. It can act as both an acid and a base, which is unique. That makes H3O plus the conjugate acid of our base, and then Cl minus is the conjugate base of our strong acid. Chlorine ions, not very good bases. They're very weak conjugate bases. Hence why we don't end up seeing the reformation of hydrochloric acid in solution. It dissociates and stays dissociated. We can also look at our trends in acids. So if you take a look, I have hydrofluoric acid, hydrochloric, bromic iodine. And we're going down group 17 here. Hopefully you recognize these from our strong acid list from before. But the reason these are strong acids, but hydrofluoric acid is actually very weak, is because the HF bond is an extremely strong bond. if you think about it, these are fairly small atoms. H, or hydrogen, only has a proton. Fluorine, very electronegative, and also very, very small in our first or second period. Excuse me. So it makes it difficult to dissociate that proton, which means it's a weak acid. So the strength of your actual bonds do have an influence on how easy it is for something to dissociate. We can also look at the addition of highly electronegative atoms to our acids. When we add electronegative atoms, we end up polarizing our electron cloud away from the acidic H bond. This weakens our bond with that hydrogen ion, making it easier to dissociate, which makes our acid stronger. So for example, I have two acids here. Our stronger acid would be HClO4 because we have 4 total oxygen atoms and a chlorine, opposed to just a chlorine and 1 oxygen. So that addition of all those electronegative atoms pull the electrons towards those oxygen and towards that chlorine, allowing that acidic H to come off easier. We're almost there. Buffers. Buffers are solutions that resist pH change. The key thing to know about them is, first, they're a mixture of usually a weak acid or a weak base and its conjugate. Usually in equal amounts. So if I were to go to the lab and make a buffer solution, I would go and grab a weak acid. I would find its conjugate salt, mix them together in equal amounts, and I have a buffer solution that's going to resist pH. Again, we can also use bases, but it has to be weak. Do not fall for the trick of when you've given a list of solutions that possibly could be buffers, and there's always a strong one listed. It's never going to be a strong acid or a strong base. It has to be weak acids and weak bases. So something not on that list that were in those 2 boxes before. Because we are dealing with weak acids and weak bases, it's an equilibrium problem again. You're going to use an ice table. You're going to need a Ka or Kb value in order to solve for the pH. Or we can use our Henderson-Hasselbalch equation. This is on your reference sheet as well. It only gives it to you in terms of the acid. But we can also do 4 weak bases. This is why you might need an ice table. Sometimes you'll be given these values right off the bat. This would be our conjugate on top, or our salt. This would be our acid concentration. This would be our conjugate acid or our base salt, actual base value. And you should be given the pK or the pKb. Maybe you have the Kb or Ka. And then you have to remember that you can just take the negative log of it to get your Ka or Kb. So essentially it comes down to knowing about your equilibriums, remembering how to use your ice table properly, and reading carefully. Do you have the initial values? Were you given the equilibrium values? What's the change? And then we have all of these different equations that can help us get to the final answer. Sometimes you'll be asked for the pH, And again, there's more than one approach here that you can use. You can use a straightforward ice table. Sometimes you're given the values where you can just plug into Hasselbalch's equation. So there's more than one way to solve. And lastly, let's just talk about our acid-base properties of salts. We have 3 types. We can have acidic salts, basic salts, and neutral salts. Starting with a neutral salt. Neutral salts are conjugates of strong acids and bases. So if we take a look, again, I've used hydrochloric acid, put it in water. We have our acid, our base. HCl donates a proton, making chlorine its conjugate base. Water is going to accept that proton, making this the conjugate acid, and water the base. Now, this is a strong acid. This is such a weak conjugate base. Extremely weak, that when we add it to water, the pH essentially stays 7. Now, this isn't always going to be the case, but whenever you see a conjugate or a salt of strong acids and bases, they are neutral. Their pH is going to stay 7. We can have basic salts. Basic salts are going to have, basic pHs, so a pH greater than 7. They are the conjugate bases of weak acids, so again, we're going to have that equilibrium arrow. And what ends up happening in solution is F-, because it's the conjugate of a weak acid, what ends up happening is this is a fairly strong base. So because it's fairly strong base, it ends up acting like a base. It's going to grab this proton, accept the proton, and we would expect a solution with a pH greater than 7. Lastly, we're going to see a similar thing with acidic salts. Acidic salts, I'm going to expect a pH less than 7. Something like ammonium. Ammonium is a fairly strong conjugate acid of ammonia, which is a weak base. So what it ends up doing is donating a proton again, and we would expect the reformation of ammonia in solution. So we end up with this equilibrium, and if we were just to drop ammonium ions into water, we would expect a pH less than 7, a slightly acidic solution. Lastly, don't forget, this is also where we can start talking about common ion effects. So if we have something like hydrofluoric acid, and then we come in and add more sodium fluoride, we'd be increasing the amount of fluoride ions in solution, and it can affect your equilibrium and also change your pH and pOH values because we're shifting this equilibrium. Hopefully this has been helpful. Please go check your answers for your homework and let me know if you have any questions.